All right, explorer, if you're like me, you're a bit bored of life down here on planet Earth. So let's mix things up. Let's travel through space in a brand new Fun Kids Science Weekly. My name is Dan. This is the show that discovers everything secret, odd and strange across the universe. We learn all those science secrets that no one else has told you before. This week, we'll learn how trees manage to stay alive and they breathe just like us.
A tree has on its leaves these tiny microscopic organs called stomata. They take in gases and they release gases. So this is a really beneficial process, not only for the tree to get nutrients, but for humans as well.
Also, our battle to find the greatest science around takes us to a teeny tiny level. We're looking at the building blocks of all life with molecular biology.
So we want to know their shape, we want to know how they fit together with each other, and we want to know what it is about their shape or their fit that makes them do their job.
And the most stunningly strange creature ever is the special star on our Dangerous Dan list. It's like something from Doctor Who. You'll want to hear all about this in a brand new Fun Kids Science Weekly. Let's start with your science in the news then. The internal parts of a prehistoric creature the size of a seed have been revealed in astonishing detail. Researchers used powerful X-rays to scan a fossil that's 520 million years old, even before the dinos. Now, the results show its microscopic blood vessels and nervous system. This thing is tiny, and it's a peek inside the body of one of the earliest ancestors of modern insects and spiders and crabs. It was found in a fossil in a pile of prehistoric grit during a study of a 500 million year old rock that was found in the north of China. And experts are amazed because the chances of finding and being able to do this was almost zero. It's amazing, isn't it, what we can learn and how we use the past to shape what we think of the future and how we've come to be here. Also, a species of butterfly, which is thought to have died out in England more than 60 years ago, is showing signs of breeding and coming back in Kent in the UK. The large tortoiseshell butterfly was common in the UK, but it disappeared in the 1960s, 60 years ago. Possibly, scientists think, because of Dutch elm disease, but they're not officially sure. But now this butterfly is making a comeback, with more than 30 spotted in the woods earlier this year, which shows ecosystems can recover if given a chance. It's amazing. We thought this butterfly had gone and suddenly it pops up again. Where has it been hiding? Did it come from nowhere? Were there one or two still around? We don't know just yet. And our final story this week, scientists have discovered dark oxygen being produced in the deep ocean, apparently by lumps of metal on the sea floor. Now, about half the oxygen that we breathe comes from the ocean, but normally by plants near the surface. That's what we thought, but this discovery is 5,000 meters deep. So, how's it being made? What's going on? Let's find out. Franz Geiger is from Northwestern University in Illinois, over in the United States. Franz, thank you for being there. Let's just start right at the beginning. What is dark oxygen?
It's oxygen that's not produced by light, hence dark. It's produced at the bottom of the deep seafloor. And when you go down there, it's completely dark, yet we find oxygen down there. And so that's why we call it dark oxygen. So
talk us through this discovery then. How have we come to find dark oxygen 5 kilometers down?
So this goes back to Professor Andrew Sweetman in Scotland from the University of Highlands and Islands. And he had been working on this for 10 years. In fact, he had made the first discovery of it 10 years ago, didn't believe his sensors, engaged other researchers that are on the team. I want to emphasize this is a big operation. Three countries are involved, the UK, Germany, and then in the US, 10 institutions. And so as more and more people got on board and helped out, the finding just kept reaffirming itself. And like any good scientist, Andrew really did a lot of control experiments and convinced himself that what we have is truly oxygen production at the seafloor. And it took 10 years to get to this point. I only joined the team about a year ago when Professor Sweetman contacted me about a possible mechanism through some work that we had done on unrelated experiments. And we had metal nanolayers, very thin layers of nickel and iron and so on, where in 2019 we had found that when we flow salt water over them, these structures generate a little bit of electricity. And so he contacted me, I'd never met him before, and said, is this a possible mechanism for production of the oxygen? And I said, probably not, because we only measured small voltages in the millivolt regime, maybe 10 millivolts on a good day. And to split seawater, you need about a volt, maybe more, like a AA battery. And I said, send over some samples. And he sent over a few kilos of these nodules. It's right here. It's the oldest thing I've ever worked with.
Okay, so it's like this craggy, jet black rock that you're showing me. How old is that, Franz?
This is the oldest thing I've ever had in my life. It's 100 million years old.
Oh, okay.
It looks like a piece of truffle, like a really big, expensive piece of truffle. And there are thousands and thousands of them down there on the ocean floor. In fact, about 3 time zones worth of nodules in this one particular area where we worked with the samples that were collected from there. That's an area west of Baja California, so the western seaboard of the US and Mexico, all the way to Hawaii. And then it even extends over to the Japanese islands. There's another big deposit south of India as well.
We began this, I said, we thought that all of our oxygen really came from photosynthesis. This is plants at the not too deep. They were taking light, they were taking carbon dioxide, they were making oxygen. You've hinted at the process that uses metal to make oxygen with a little bit of electricity. Can you just build on that for us? How do we think this oxygen was made way down deep in the ocean?
So these are structures that grow at a really slow pace. You can think of it almost like a really super slow game of Tetris with, particles coming down from top of the ocean, very, very slowly accumulating through accretion processes. And they grow at about 1 millimeter per million years. So it's the slowest process that we know on Earth. And when they grow, they don't grow uniformly. When you cut them open, they have the appearance almost of an onion or the ring structure when you date a tree. And so the distribution of the metals is not uniform in these onion-like structures. And there's more nickel on one part of the nodule than on the other part of the nodule. There's a higher concentration of perhaps cobalt over here versus there. And it's very well known, this goes back to the famous Italian scientist Alessandro Volta, who built the original voltaic pile, that when you have gradients of these metals, and especially spatially different arrangements of different metals, you can build a battery. And while each of these that we measured has small voltages, 10 millivolts, 50 millivolts, 100 millivolts. The biggest was 950 millivolts. That is the king of the court so far. When you line them up and they're connected to one another, which the pictures from the abyssal seafloor clearly show their connectivity, then these voltages add up, just like when you take 2 AA batteries and instead of 1.5 volts, you get 3 volts. And you can triple the voltage when you take 3 AA batteries, and so on and so forth.
Wow. That's dark oxygen, made by metal 5 kilometres down. Franz Geiger from Northwestern University. Over in the States, thank you for joining us.
Thank you so much for having us on the show.
Thank you very much to Franz Geiger. Very smart name, Franz Geiger. What a genius. Thank you for coming on the show. We'll have more experts on in just a little bit. One of them will answer your question. Let's do that right now. I love when you send your science questions to me. It's my favourite thing that we do. It gives me the chance to really do the digging, to become a science Sherlock Holmes and figure out what it is that you're thinking and what you want to know. Best way that you can leave a question is as a voice note on the free Fun Kids app or at funkidslive.com. Here is a message sent in to me from Jessie in Dorset, and it's a big one. Jessie wants to know, where did the first energy come from? If it was the first thing ever, if it was around before the universe, if it started it all off, where did it come from? It's a huge question. The fact is, we don't officially know. I'm not sure we ever will, really, not soon anyway. We have ideas, we have good guesses, but we're not 100%. The problem is there is a science law that says energy can't be created or destroyed. It changes from one form to another. I mean, think of if your mum or dad ever does a bonfire in the back garden. It gets really hot, that's heat energy, and then it shines bright, so that heat energy becomes light energy. So all the energy we have has always been around. But where did it come from? That's what Jesse wants to know, and that's what a lot of scientists want to know too. According to the general theory, there was the Big Bang. The universe began as a singularity, something teeny tiny that came pretty much from nothing. This happened about 13.8 billion years ago. And inside that tiny speck of almost nothingness, all the mass and all the energy of the whole universe was there, squashed into this teeny point. And the Big Bang started a rapid expansion. It led to the formation of particles and atoms and stars and galaxies and everything else that we have. The energy that we have in the universe today came from that initial state. Here's the thing. Maybe, though, the laws of energy conversion only exist in our universe. That rule we spoke about earlier, that energy is always around, maybe that only is true in this universe. Maybe it doesn't apply to other places that the universe might have come from. Blows your mind trying to think of that. And the true answer is that the origin of the first energy remains one of the biggest mysteries scientists are trying to sort out. But thank you for the question, Jesse. Let's get on another one as a voice note. This one was from Zayn. What do you have, Zayn?
Why do trees breathe in carbon dioxide?
All right, Zayn, thank you so much for your question. Why do trees breathe in carbon dioxide? Let's find out with one of our favourites. Laurie Dove is here from How Stuff Works. So, Laurie, trees, let's start with, why do they breathe in carbon dioxide in the first place?
That is such a great question. Trees, as you might imagine, can't get up and go walk to their next meal, so they had to devise a way to make it themselves. And the way they've learned to put on this chef's hat is to find their food while they're rooted in place. And how they do that is breathing in that carbon dioxide or CO2 and converting it through a chemical process into food.
So that's why they do it, but trees don't have any lungs. So they don't have mouths. They're not breathing it like you and I would breathe. How are they doing that?
That is exactly right. They do still use a process that we refer to as respiration. So a tree has on its leaves these tiny microscopic organs called stomata. And the stomata, they take in gases and they release gases. So this is a really beneficial process, not only for the tree to get nutrients, but for humans as well. So the tree will take in the carbon dioxide and through a process called photosynthesis, use sunlight and other gases and convert that into the nutrients it needs like nitrogen and phosphorus. But the best part, especially for humans, is that the tree breathes out, essentially, oxygen.
So this is, this brilliant process. Carbon dioxide, water, and some sunlight all work together to keep them alive. But the interesting thing, Laurie, as well, is plants are able to do this underwater, aren't they, at some levels?
Yes, that is really interesting because the plants that we have on land, trees especially, produce probably about 28 to 30% of the world's oxygen. But the rest of it, which is a very large amount, comes from plants that are ocean plants like phytoplankton and things like that, that also emit that oxygen and are responsible for the air that we breathe.
What do we know about how trees are able to do that through winter and the fall when their leaves drop off? That must make it harder for them to breathe.
Yes. So deciduous trees like that, this process is always continuing. So when a tree takes in carbon dioxide, which, by the way, is one of the dominant gases that's responsible for warming the earth right now, they will store that carbon dioxide in the trunk. And when the tree lives, the carbon dioxide just stays in there. That's why trees, in a way, go dormant in the winter when they're dropping their leaves and they're not actively taking in that growth cycle, but they are still alive and thriving. The other interesting thing is that when those leaves fall, they are broken down by soil microbes that decompose the leaves. And when that happens, this releases carbon dioxide back into the atmosphere, but very, very slowly over time. The same principle applies to a tree that dies. So let's say a tree dies and falls over in the woods and it is left to decompose there. It will also slowly over time release that carbon dioxide as it rots. But let's say you make the tree into furniture. It stays trapped as long as that furniture is viable and not left to rot somewhere as well.
Well, Zayn, and that is why and how trees breathe in carbon dioxide. Laurie Dove, thank you for joining us.
Thank you. It's my pleasure.
Thank you very much to Laurie Dove, friend of the show. We love getting Laurie on. If you have anything sciencey that you want answered next week on the podcast, make sure you leave it as a voice note for me on the free Fun Kids app. You can do it too at funkidslive.com. Let's dive into this week's Dangerous Dan, where we take a look at the most weird, strange, mean, cruel, devastatingly deadly things in the universe. And here we're taking a peek at one of the most spectacularly strange and stunning insects in the world. You'll find the Saddleback Caterpillar around the east of the USA, in woods and gardens, eating shrubs and trees. Now, it looks incredible. If you can, get a picture. I don't know if I can describe it well enough and do it justice, just how stunning and amazingly strange this creature is. It's got a bright green body with a brown patch on its back, which looks like a saddle. Gives it the name Saddleback Caterpillar. Even better than that, the front and the back of the body are covered in these spiny horns, big things that stick out with spikes all around it. It looks like a cross between a cactus and something from Doctor Who. And those spiky spines cause damage. Inside is venom that causes intense pain and swelling. It makes you feel very sick. It can lead to other allergic reactions, which is why it's so bright. One thing we've learned from the Science Weekly is that quite often the brighter an animal is, the more dangerous it is, the more poisonous it is, and it doesn't really want you to get near it. That's particularly true of insects. You see, it takes a lot of energy for some poisonous creatures to harm you. They really don't want to do it. They don't even want to take the risk that they might get eaten. So they are bright to warn off predators, to say, look at me, I'm really bright, don't come near me because I will sting you, I will cause you tremendous harm. Now, this caterpillar, the saddleback, it eventually will transform into a moth. The sad thing is, the moth is boring and brown. So it's only really, we'll stick with the Saddleback Caterpillar. Spectacularly strange, it's utterly stunning, and it goes straight on our Dangerous Dan list. This week on Battle of the Sciences, where we try to discover the very greatest science around, we've got Sam McKeon fighting to be first in every field. Sam is from Manchester Metropolitan University, and we're looking at the building blocks of who you are. It's molecular biology. Sam, thank you for joining us. We start with 1 minute. You have 60 seconds to tell us why your science is the best, and that minute starts in 3, 2, 1. Go!
Molecular biology is studying all the important molecules in the body. Now, your molecules are the bits and pieces in your cells made from DNA, RNA that constitute proteins. Now, what are proteins? Proteins are the molecules that do all the important jobs in your body, everything from the structure of your skin and bones to helping fight off diseases. And the interesting thing about proteins is they're a bit like snowflakes. Snowflakes are all different shapes, as I'm sure you know. Well, proteins are also all different shapes. But just imagine that the shape of the protein tells you what job it does. These are a bit like keys. Different keys are different shapes and they open different doors. Well, different proteins are different shapes and they do different jobs in your body. But also, just like Lego, they can build on top of one another to make super proteins, bigger ones that do even bigger jobs.
And there's your minute, Sam. That's your minute done. I think you pushed it close to the wire. But what are you discovering when you go into work as a molecular biologist, when you no doubt put on your lab coat and your eyes are ready to peer through a microscope all day, what are you looking to discover? What are you researching through the day?
So we want to know their shape. We want to know how they fit together with each other. And we want to know what it is about their shape or their fit that makes them do their job. And there's different ways of finding that out. You can use X-rays. You can make these proteins into crystals so they stay still, and then you can shoot X-rays at them to find out their shape. You can use electron microscopy, or you can use cryogenics, which is where you freeze them instantly like ice, so it stays in the shape really still. There's lots of ways of doing it. Or you can use artificial intelligence to make computers figure out how they make their shapes. Now, once we know their shape, we can figure out their job. And once we figure out how their job is involved in the body, we can make all kinds of new medicines, new drugs to help fight different diseases and or to help make medicine better.
Here's a question about DNA and the double helix that you've mentioned that I've always wondered. So as you're listening, you might have seen a picture of the double helix of a DNA. It looks like a ladder that's twisting round. It's got all these rungs, and the rungs are made up of different parts of information. How true to life is that, Sam? Is that actually how DNA looks? And what's it doing? Is it swimming in liquid through us? Is it inside the middle of cells? Like, just try and explain it, because it melts my mind a little bit.
Almost all of the DNA is in the nucleus of your cell. Not all of it, but almost all of it. And yes, it really does look like that. And that's one of my favorite things about molecular biology, is it's very beautiful. I think DNA is very, very beautiful. And just like snowflakes are beautiful, I think proteins are quite beautiful as well when you see pictures of them. Now, it's amazing how nature works, but when you're looking at the individual bits of your body that do all these important jobs, that spiral ladder of the DNA double helix inside the nucleus of your cell is so tightly wrapped up. But if you were to stretch it out end to end, all the DNA in all the cells in your body, if you were to stretch it out in a straight line, it would go to the moon and back.
Let me throw you forward 30, 40, 50 years, whatever it is, by the time that you hang up your cryogenics and your microscope. When you're done with your science, Sam, what's the one question that you really want to find out? What do you really want to know and have answered by the time that you call it a day?
That's a great question. The first answer that pops into my head is there's some really, really weird animals on Earth. And I just think it's crazy how their bodies can work the way they do. And I would love to know the answer to how they can do the things that they do. So there are these creatures called water bears. And they are really, really ugly. They're tiny. That's their nickname. Their real animal name is tardigrade. And they can survive in space outside of a spaceship, which is crazy to think that any living organism can do that. They can survive with no oxygen. They can survive at minus 200 degrees or plus 200 degrees. And they can survive in the strongest radiation. And I would love to know how their bodies work, how their cells work. So it would be amazing to find out exactly how the molecules in their bodies allow them to live in such a dangerous, crazy environment. And there's lots of animals like that. Bacteria and archaea that can survive in volcanoes. Yeah, I'd love to know that sort of thing.
Well, do you think that is first for the whole science? Is that the best ever? It's been a brilliant case. We ran through a lot with Sam McKee from Manchester Metropolitan University. Sam, thank you for joining us.
Thank you for having me. It's been good fun.
Earlier on in the show, we heard from Franz Geiger. It's a very sciencey name because a Geiger counter is what experts use to measure radiation. Anyway, and Franz was talking to us all about finding oxygen at the very bottom of the sea. I thought we would head back there now with an episode from our brilliant Marina Ventura series. This is her ocean adventure where she's travelling right the way through the sea to learn all about the strange creatures that lurk nearby. She is an animal genius, joined by her digital sidekick Map app. She is 7,000 metres in a submarine, looking at some odd beasts at the very bottom.
Konnichiwa, adventurers. That's Japanese for hello because we're in the Japanese Sea, in a submarine. We're off to the very bottom of the ocean to check out some of the strangest life in the sea. Let's batten down the hatches and dive down. 1,000 meters, 2,000, 3,000, and down we go. Now we're at a sensational 7,000 meters under the water, and the pressure down here is immense. Good job this sub is tough. If you've ever carried a bucket of water, you'll know that water is heavy stuff. And down here, all that water above us is as heavy as having over 1,600 elephants standing on top of us. Now, elephants couldn't ever live down here. In fact, very few life forms can survive the seriously squashing pressure. But if we look very carefully, we can see some amazing life forms that do thrive down here. Like this funny swarm of Limparidae or snailfish. Strange, pale swimmers that like it a lot down here. In fact, it's a feeding frenzy. As we move on, we can see some hydrothermal vents, or black smokers. We'd better not get too close. Those boiling hot volcanoes are erupting under the water, and not many things can take those temperatures without frying. But some shellfish like the challenge. Over there are some happy clams. They must like the steam treatment. These clams are incredibly weird. Their bodies work in a totally different way to most things on Earth. They have special bacteria in their gills that can absorb energy from the sulfuric fluids coming from the vents. As you can see, it's a weird and wonderful landscape down here. Let's boot up my map app to find out more. It's the electronic essential for every explorer and is in my rucksack here somewhere. That's not it. I thought I'd packed it near the top. That's my crampons. Great for mountains, less great down here. Ah, here it is.
Hello. Oh, we're underwater. You want a deep sea snippet?
Yes, please. It's so weird down here. You must have some great facts for us.
Of course. Here's a clue. That's a whale, of course. They can't live at these depths. But when a whale dies, its body falls to the bottom of the sea and it provides a feast for all sorts of marine life and bacteria. These whale falls, as they are called, act as an oasis of food in the hostile deep sea environment. But many of the tiny organisms that are found around them are very puzzling to scientists because we don't really know how they find these watery feasts or how they survive between meals.
Amazing! Make sure you join me and MapApp next time when we'll find out more about the mysteries of the deep. Toodle pip, adventurers!
And that is it for this week's Fun Kids Science Weekly. We will be back same time next week answering loads more of your questions. If you have anything sciencey, make sure you leave it as a voice note for me on the free Fun Kids app or at funkidslive.com. You've heard Marina Ventura today. We've got loads more brilliant podcasts that you can listen to on Google, Apple, Spotify, wherever you get your shows too. And remember, if you are subscribed to Fun Kids Podcast Plus, you get over 30 of your favourite Fun Kids podcasts completely ad-free and bonus episodes. You'll be the only one that can hear them. Even more exclusive stuff from the shows that you love. Find out more at funkidslive.com. And Fun Kids, we're our children's radio station from the UK. Listen all over the country, on the app, on our website, and if you've got a smart speaker, wake it up and ask it to play Fun Kids.